In this lecture, we talk about functional dependencies which play a crucial role in the design of databases or fine-tuning of the databases. Using ER modeling, we can create the conceptual design of the database, and once we arrive at a final conceptual design, we can convert that ER diagram into the schemas based on the entity sets and the relationships that are defined in the ER diagram. We can create schemas. And based on the requirement analysis, the information that is collected in the requirement analysis is useful to define the integrity constraints on the attributes of the schemas. Now, once everything is done, is it the final one? No. There are certain issues still which are going to create problems for us. The first issue is redundancy. That is duplication of data, unnecessary duplication of the data, and the problems that are caused by that redundancy. We need to address that first. Because if we can understand that the problems that are caused by the redundancy, then we can find solutions for that, and we can fine-tune the database further in a much more optimized way or effective way. Redundancy may be caused in several ways. Here in this example, if you look at two small tables, the student ID is repeated and concession is repeated. So two columns are repeated across two tables. This is one kind of redundancy, duplicate information. Not only that, another kind of redundancy that you can observe that in the first table, category A, the fees is 1000, category B fees is 2000, and category A, third case, category A is 1000. So wherever category A appears, the fees is fixed 1000 rupees, and wherever category B appears, the fees is 2000 rupees. This is some kind of information that is there available in the table. So this is another kind of redundancy, because wherever A appears, 1000 appears. It's a known fact. So repeatedly storing 1000 whenever A appears is some kind of redundancy, another kind of redundancy. This is an example that we have seen. Imagine a table consisting of 10,000 rows with such kind of information. So imagine the space that it occupies is one issue. Not only space, but there are three types of anomalies that may creep in because of such kind of repetitions or redundancy. They can be classified as update anomalies, delete anomalies, and insertion anomalies. If we first look into the update anomalies, suppose a particular attribute is repeated at 3 or 4 locations across different tables. Then what happens whenever the value of the attribute in one table is updated, and all its copies must be updated. Otherwise, even if we fail to update one copy, then any query that operates on that table returns useless information. It's unupdated information. So that is one thing. So whenever attribute value is repeated, every copy of that, wherever it appears on the database, it has to be updated. The consistency of the database will be lost even if we forgot to update one value. For example, here in this small example that we consider, look at the concession. 101, 102, 103, the student IDs and concessions are yes, no, and yes. Initially, let us assume that the student with 102 number student ID has no concession. Now, because of some rule, he was given concession. Then we will update the value of no to S. The status of concession will be updated from no to S. And if you forgot to update the information in the second table, refund status, then still that student will not get refund. Even though it is updated in the first table, if it is not updated, because the same information is repeated here, if it is not updated, he will not get the refund. So in the list of refund, he will not be reflected, whereas in the list of students who got concession, he will appear. This is one kind of anomaly. The second one is insertion anomaly, where certain values, if you want to insert, certain other values are also be forced to be inserted. Again, for example, in this case, if you look at the bank account number, it may be possible that all the students may not have bank account numbers. Suppose if one new student has been admitted and category is filled, fee is filled, for bank account I have to enter null because you don't have the bank account number. So this is because bank account number is linked with all other data unnecessarily. So because of this linking, the unnecessary data has to be inserted into this, or otherwise I cannot insert the data. I cannot insert the row, complete row, without giving any information to the bank account number. So I have to insert null there. This is one kind of insertion anomaly that may creep in. Now if we look at deletion anomaly, it looks peculiar. Suppose in the first table, if I delete the second row, the student with the student ID 102 has left the institution and his details are deleted from the table. Let us assume that. Then what happens is, if I delete the second row 102 category B 2000 and the other details, fine, nothing looks difficult. But the problem is, let us assume that he is the only student who joined in category B and he left the college. So the complete details are removed from the table, Then what is the fee for category B? Can we get the answer from the remaining table? Once we delete the second row, can we get the answer for this? No, because that information is lost. So this is because of the repetition, redundancy, unnecessary redundancy that is, and the design of the table. So this kind of loss of data may also be there in case of deletions. To deal with the problems that are associated with such kind of redundancies, we need to understand the data in much more deeper sense. For example, in this case, we can observe that whenever category A is there, 1000 is fixed. So for all the values of A, 1000 is the value. And whenever category B is there, 2000 is a fee. So some kind of relationship is there between the attributes. This is exactly what is called a functional dependency among the attributes that we need to understand when we collect the information in the requirement analysis. So if we are able to find out such kind of relationships among the sets of attributes, sometimes it may be between just two attributes, or sometimes it may be between a set of attributes with some other set of attributes. It all depends on the data. So we need to understand in a much more deeper sense how the attributes are depending on each other. Because since the redundancy is there, how can we deal with this? One way of dealing with this is decompose the table into smaller ones to avoid such things. This is one solution. But how do we decompose? What is a factor that influences the decomposition? Simply by going by the numbers is useless. So there should be some way to identify the decomposition principle or procedure. Functional dependencies are going to help us in this aspect. If we can identify the functional dependencies in the requirement analysis, based on the functional dependencies, we can divide the tables into smaller ones so that the redundancy is minimized and the problems that are associated with such kind of redundancies can be minimized. We observe that there is a natural relationship between category and fee in the table that we have given in the last slide. That is exactly what is called a functional dependency, and let us understand it more mathematically. Actual definition of the functional dependency. Let us start with a schema. Let R be a schema with certain set of attributes. Let X and Y be two non-empty sets of attributes in R, and let R of R denotes the instance of R. Instance is table together with the data at any point of time. So a schema may have different instances. Now functional dependency is said to hold between X and Y such that X functionally determines Y if for every pair of tuples Ti Tj, for every pair of tuples Ti Tj or T1 T2 that holds on R of R, if these values of the attributes in the set X are same for the pair of tuples T1 and T2, then it should tautologically imply, or it should imply immediately, that the values of the attributes in Y, set Y, should also be same for that pair of tuples. And this should happen for every pair of tuples, for every instance of R of R. This is how we define the functional dependency. And one important issue here is the functional dependencies are not based on the data that is inserted in the table. No, it should be identified at the definition of the schema itself. We need to identify the functional dependencies. So functional dependencies are identified at the requirement analysis phase, not at the data insertion phase. Now, given a schema, once we identify the set of functional dependencies at the requirement analysis phase, is that set of functional dependencies are final, or are there any functional dependencies that are indirectly holding because of the existing or identified functional dependencies? To understand this, there is a concept called Armstrong's axioms. Certain axioms were developed by Armstrong, a scientist, who has given us a set of rules. Based on these three rules, we can identify all such functional dependencies that can be implied by a given set of functional dependencies on a schema R. They are very simple. First one is reflexivity. Whenever y is subset of x, a set of attributes y is subset of x, then x functionally determines y is automatic, which is a trivial functional dependency. The second one is augmentation. Whenever x functionally determines y, then the set of attributes in the sets x and z, xz functionally determines the set of attributes in yz, the union of the sets y and z. So this is called augmentation. The third one is transitivity. Whenever x functionally determines y and y functionally determines z, then it implies that x functionally determines z. The justification of these three rules is very simple. You can clearly observe that for any pair of tuples, if the values of attributes in x are same, since y is part of that in the reflexivity part, since y is already part of that, the values of y are also same for that pair of tuples. So reflexivity is justified. Similarly, if we go for the augmentation, it is known that x then y holds. That is, for every pair of tuples ti, tj, the values of x are same. Whenever they are same, y are also same. Now you are appending the attributes in the set z. So whenever for every pair of tuples, the values of the attributes in both x and z, union of x and z, same, then for y they are already same because of the given x then y, and they should also be same for z. That's augmentation rule. Transitivity is trivial. Whenever for any pair of tuples x values are same, then y values are same, and whenever for a pair of tuples y values are same, z values are same, it automatically implies that the pair of tuples, whenever x values are same, z values are also same. So that seems to be very simple, but they are very powerful rules to identify the functional dependencies that are implied by the given set of functional dependencies. Importance of Armstrong's axioms is that they are sound and complete. That means they will generate only functional dependencies that are in F plus, or closure of F. They will not generate any outside functional dependencies. And complete in the sense they are the repeated application of these rules will produce all possible functional dependencies. That's how we treat them as sound and complete. Look into the two more rules which are not part of the Armstrong's axioms rules, but these are useful in deriving other rules in F plus. But these are not independent rules. They can be derived from Armstrong's axioms. One is a union rule, that if x function determines y and x function determines z, if we know that, if it is given that, then x function determines yz, the union of all the attributes of y and z. It's trivial. Similarly, decomposition. If x function determines y and z, union of yz, then we can decompose into two functional dependencies in the form that x function determines y and x function determines z. This is called union and decomposition rules. They can be used to generate functional dependencies in the closure of F. Now we'll look into one important aspect here, that given a schema, we have a set of candidate keys. We can say that every candidate key determines all the attributes. For example, if you fix one of the candidate keys as a primary key, that primary key determines all the attributes. An interesting fact here is that when do you say that a functional dependency fails? If you can find two tuples Ti, Tj such that even though the values of attributes of X are same for T1, Ti, Tj, if they differ on the values of attributes of Y, if you can find at least one such pair of tuples, then we can say that the function dependency fails. Now in this aspect, since for a primary key you don't get a repetition of the value, you can't find a pair of tuples where that function dependency fails. So that's why every candidate key determines all the attributes in the schema. That is one important observation that we can make. Now, finally, we'll see an example here. Let R be a schema with 4 attributes A, B, C, D, and given set of functional dependencies A then B, B, C then D, and A then C are the functional dependencies that holds. It is given. Let us assume. Then what are the other functional dependencies that holds indirectly? So then A then B holds, or A functional determines B holds. By augmentation rule, AC functional determines BC, because C can be augmented on either side. Now A then C holds, and A then A holds trivially. So A then AC holds again by union rule, and AC then BC holds just now we have observed, and BC then D is already given. So if I combine these three rules by transitivity, I can say that A function determines D. So it is an indirect functional dependency that holds, though it is not given directly. And finally, the reflexivity rule can also be observed that since B is part of BC, BC functional determines B is trivial. This is how we can use the rules and compose the rules in different forms, and we can generate all possible functional dependencies, which is called the closure of F.